We're going to take a look at some of the properties that distinguish small molecules such as monomers with macromolecules like polymers. Of course, polymers are long chain molecules composed of monomers that have been enchained together by forming covalent bonds with each other. If we think about some simple activities you might be familiar with, such as taking a glass of cola and pouring it, compared to taking a jar of molasses and pouring it, we encounter a property called viscosity. The molasses is much thicker and harder to pour than the cola. And there are a number of reasons for that, but one of the things that distinguishes the molasses from the cola is that the sugars in the cola are generally small molecules, they're monosaccharides. But in the molasses, there are a lot of polysaccharides. There are polymers, sugars in polymer form. And that's part of the reason for the thickness or the high viscosity of the molasses compared to the cola. If we've got a solid material, if you take a stone and you take an eraser of the same size, you can stretch and bend and twist the eraser, but you can't do that with the stone. And part of the difference in that behavior is due to the polymers that make up the eraser. These properties stem from the chain structure of polymers, and they're related to both chain flow, the fact that these chains can slide past each other. So when you twist the eraser, the polymer chains that make up the eraser are sliding past each other, but also a sort of a balancing factor, chain entanglement, the fact that these chains interact with each other. They might be literally tangled up together or interacting via intermolecular forces, for instance. And that's what causes the eraser, once you've twisted it, to snap back into shape, because these chains are pulling the material back into its original form. Now, there's a unique sort of property of polymers called glass transition. It's a phase change in which polymers can go from being a rubbery sort of material to what's called a glassy material. And it's not glassy like a glass window, but it is more brittle and stiffer, like a window is. And this transition is related to the amount of chain flow, or the ease of chain flow in the material. So an eraser is made of a polymer that is in its rubbery phase. There's free chain flow, so that the eraser can be twisted and bent. But a pen is often made of plastic that's more in a glassy phase. It has limited chain flow, and so it holds its shape much more strongly. Now, the glass transition is related to the free volume around the chain. So the more room there is around these chains, the more easily they can slide past each other. But it's also related to how much interaction there is between the chains. So chains that are interacting very strongly don't move past each other as easily. And polymers can change from being in the rubbery phase to being in the glassy phase just by changing temperature. So at a higher temperature, the chains maybe have room to flow past each other, but at a lower temperature, because solids contract as you cool them down, eventually the chains are going to get too tightly packed together. They're unable to flow past each other, and now they become glassy. So just to look at a couple of examples, polyethylene is a pretty common polymer. It's used in things like water bottles, for instance. And we think of that sort of plastic as being rigid enough to hold its form, but easily crushable. You can change its shape with your bare hands pretty easily. Those chains interact with each other through intermolecular forces. Now, the intermolecular force here is fairly weak. It's a London dispersion force. There's not a whole lot to hang on to here. If we take something sort of similar, polystyrene, it's also a nonpolar polymer. it doesn't have any dipoles or anything. The intermolecular forces aren't that strong between the polystyrene chains. But the fact that we've got these benzene groups coming off the polystyrene gives that polymer a lot more surface area. And so the London dispersion forces between these neighboring chains get much, much stronger. And the glass transition increases about 200 degrees Celsius, going from polyethylene to polystyrene. And familiar things that might be made from polystyrene include things like the cap on that water bottle, which is much harder to crush than the water bottle itself. Now, one other way that's related that polymers can